Got it? Ahem. I will begin with a word of prayer. Ahem. I choose to do this. Dear Father, we thank you for this day. I thank you for these students and their enthusiasm over math and other things. And I just pray that you be this day, help us to understand a little bit more about linear transformations and perhaps start determinants. Lord, in your name I pray. Amen. All right, so I think what I'll do is just start by talking about coordinates in Rn. Now, I'm choosing Rn just to keep it real. Everything I'm saying here would equally well make sense for Fn, where F was a field. Yes, sir?
Today, if there's any time, could you explain the isomorphic homework questions a little bit more? 85 and 86?
Yeah. Yep. I mean, I asked you to find isomorphisms. What that means is to find an isomorphism.
Right. They were challenging, though.
Done. Yeah, that's it.
That part we got. We got that part.
I'll try to work an example. So we let beta equals to, let's say, v1, v2, ... vn, a basis. All right. And then we can study how do you find a, Rn is so special, much like Fn. I mean, everything I'm saying here would just as well be true for Fn, but I'm going to keep it real. So the coordinate map in Rn is so special. It's so special. So if I have x, all right, and x is equal to, let's say, c1v1 plus c2v2 plus plus cn_vn. By definition, right? By definition, what do we have? The coordinate vector of x is what? Right, it's the coefficients that appear in the linear combination that you need to construct the vector from the basis. That's unique because the basis is assumed to be linearly independent. Now, is there any way we can write this in some kind of like neat way? Well, yeah. This, of course, is the same as the matrix v1, v2, vn, which is an n by n matrix, by the way. Concatenation of n column vectors gives me a square matrix, n by n, and times the c1, c2, cn. So, what would be a nice name for this square matrix I just wrote? What it is we're taking the basis, right, and we're making it into a matrix. So the standard notation for this, when you're talking about a set of vectors in Rn, it makes sense to just put some brackets around it and say beta, like that. This is the matrix which is formed from the basis. Now, I wouldn't want to do that in the abstract case unless I develop some more formalism that I haven't at the moment developed. Right? I don't know how to look at a matrix. I mean, I guess I do know how to look at a matrix of polynomials, but I don't have as many results there developed. So anyway, this makes sense. That's the n by n matrix, which is right here. This is beta, okay? And this is what? Well, I could also write this as the coordinate vector of x beta, right? So we have x is equal to matrix of beta times coordinate vector of x, right? Therefore, the coordinate vector of x is just the inverse of that times x. In other words, we have this like cool little theorem. The coordinate mapping with respect to the beta basis in Rn of x is simply equal to multiplication by the inverse of the basis matrix. Or if you want me to write it even more sneakily, phi beta is left multiplication by beta inverse. That's very nice. So to find coordinate vectors, coordinate map in Rn for a non-standard basis is not such a big deal. For example, if I want to find the coordinate map, say from R2 to R2, where the basis I'm going to look at is, I don't know, whatever you want. 1, 2, 3, 4. How about that? I didn't make that homework, did I? I'm a creature of habit. I'm not trying to do the same one as your homework. If I have, you'll have to forgive me. So all I got to do, what's that? I'm equipped to forgive. Well, yeah, I do have to let you earn your grade, though. So beta inverse is the inverse of 1, 2, 3, 4. Okay, what's the inverse of this? You are using the formula, yes? Very good. So that's 4 minus 6. Flip the diagonals. Minuses on the off diagonals. So you got what? You got, this is minus a half, right? So I got minus 2, 3 halves, 1, and minus 1 half if I didn't do it wrong. We could check, right? Multiply this matrix times that. I get minus 2 plus 3 is 1. I get minus 4 plus 4 is 0. 3 halves minus 3 halves, 0. 2, 3 minus 2 is 1. Yep, multiply this times this, you get the identity matrix. We remembered the formula, right? Great. So then, what is the coordinate of, say, if I look at the coordinates of x and y, what are they? Looks like minus 2x plus 3 halves y, and here we've got x minus y. By the way, these are, so if I'm using x and y as the Cartesian coordinates, as I am here, right? You might say that what we're defining are new coordinates, right? In fact, we are defining new coordinates. And to give these a name, you might give these a name. You might call this x bar and y bar. So we just found the coordinate change formula. Yes, sir?
Should we make mine x minus y over 2, right?
Oh, thank you. Is that, what's that?
Bonus point?
Oh, as we've discussed, Adam, there was one, but then, much like the wave function collapsing, with your comment, you destroyed it. So that's the coordinate map here. Let me just take a second to say what this means. So you could even write it this way. X bar is, minus 2x plus 3 halves y, and y bar is equal to x minus 1 half y. These are the formulas for the coordinate change from the Cartesian coordinates to this non-standard coordinate system. Let me even attempt a picture. So like if I take a point, right? Say this one, 2 and 3. To say that's 2, 3 means what? That means that I can take 2 copies of E1, right? And 3 copies of E2 and get there, right? Stupid obligatory comment. If gamma is E1, E2, right? What's the coordinate vector of 2, 3 with respect to the gamma basis? It's 2, 3, yes. And by the way, what's the coordinate mapping? Phi gamma of x is equal to what? Gamma inverse of x, which is what? E1, E2, inverse x, which is, by the way, Ix, which is, by the way, x. Okay. We didn't need this concept before we were looking at non-standard bases, right? So I can, on the one hand, get to the point 2, 3 by taking 2 E1s and 3 E2s, but what would the x bar, y bar coordinates be? So what's the coordinate? What's 2, 3, and the beta coordinates is what? minus 4 plus 9/2, yeah? Oh, thank you. I know what I've done. And then what's the other one? Yeah, 2 minus, yeah. Can you give me what's the numerics on that? Let's say 1/2. And this is what? 1/2. Oh, 1/2, 1/2? Huh, cool. All right. What geometric, now at the point we'll suffer the inexactness of my picture. But what direction, so like, what this says then, of course, is that 2, 3 is 1/2 times the first vector, which was 1, 2, plus 1/2 times the second vector in the basis, which is 3, 4. Let's see here, 1, 2 would be something like this, right? So this would be 1, 2, roughly speaking. So like half of that, right? That would be 1/2 of, I need to give this a name. Let me call this one F1. Oh, let me call it E1 bar. Let me call this E2 bar. So 1/2 of E1 bar. And then what's the other one? 3, 4, right? What does 3, 4 look like? It's like this direction, right? So I can't do it. My picture isn't quite, I don't know, it's something like this. If I was using graph paper, maybe we could do better, but the point is, 2, 3 is a specific vector in the plane, right? But you've got different ways of reaching it with the standard basis versus with the non-standard basis. And the relation between the two is captured by multiplication by the inverse of the basis matrix. This or something like this is a reasonable test question because inversion of a 2 by 2 matrix is easy. If I make it a 3-dimensional question, all of a sudden it's eaten half of the time for the test, right? Because you got to invert a 3 by 3 matrix. Anyway. All right, so there's an example. Now what I want to talk to you about is the problem of coordinate change, right? I guess the first thing you might think about is if you have a vector space over a field F, right? And you have basis beta and beta bar are both bases for V, right? And X is an element of V, then how are the coordinate vector of X with respect to beta and the coordinate vector of X with respect to beta bar connected, related? Okay, that's the question. And so you're starting to draw a picture. Maybe a picture will guide our thinking. So here's the vector space V up here. Here's a vector in it. Let's call it X. All right. And I want to say X is equal to what? Something like C1 V1 plus C2 V2 plus da 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 plus Cn Vn, or it's equal to C1 bar V1 bar plus C2 bar V2 bar plus da 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 plus Cn bar Vn bar. This is my typical lazy notation to capture a basis and another basis at the same time. I like this notation. It's somewhat intuitive. Like I use everything without bars for my first basis, everything with bars for the second basis. So it's, it's a nice notation. Right, so in this notation, we'd have what? Coordinate of X with respect to beta, C1, C2, Cn. The coordinate of X with respect to beta bar would be C1 bar, C2 bar, Cn bar. Okay. How do I relate these? Let me show you how to figure it out with a diagram. So what I'll do is think about it this way. Down here, I have Fn, and I have the mapping phi beta, right? On the other side, I also have a copy of Fn, and I have the coordinate mapping phi beta bar. I guess I could even think of it as the same copy of Fn if I want. I don't know. I'm thinking of them as disconnected. So how do I relate then? Phi. So you're like, you can go to get from here to here, you do what? You said phi beta, so you could go from here to here, I would do phi beta bar composed with phi beta inverse, is that right? I think that's right. Let's see, let's try it out. Let's take it for a spin. If I start with, down here, the coordinate vector of x with respect to beta, does this mapping take me over here to the coordinate of x with respect to beta bar? Does it work? Let's see if his guess is right. So we have phi beta bar composed with phi beta inverse. I'm going to feed that the coordinate vector of x with respect to the beta basis, right? So in other words, we're looking at phi beta bar of phi beta inverse, right? Of what? Now I wrote it coordinate vector of x with respect to beta, but what's the other way we can write that in terms of a mapping? My other notational choice for this is just that that's phi beta of x, right? That's just our notation. We can either denote the coordinate vector of x with bracket with sub beta or with phi beta of x. What is this, though? That's just x again, right? This is the composition of a mapping and its inverse. So I'm just back to x again. And you can see that his guess, in fact, was very, very good. See, because that is exactly the coordinate vector of x with respect to the beta bar basis. And this is very, very nice because this mapping that you guessed, phi beta bar composed with phi beta inverse, what kind of mapping is that? Notice that phi beta bar composed with phi beta inverse is an element of the linear transformations on Fn. It's a mapping from Fn to Fn. By the fundamental theorem of linear algebra, we can express that as a matrix multiplication. Right? So let me collect our thoughts here. What we have is we have that phi beta bar composed with phi beta inverse, that when it acts on x beta is equal to x beta bar. That's what we just proved. What have I done? It's not me. Okay. That is a relief. Let's see here. So, do you guys agree with this? Are we all on the same page here? But this is a linear transformation on Fn, right? So I can justifiably rewrite this as what you've got is you've got the matrix of phi beta bar composed with phi beta inverse multiplied by x coordinate, the beta coordinate, gives you the beta bar coordinate. And so there you go. Now, typically people just call this thing like p beta beta bar or something like that. I mean, notational choices vary, but so here I'm saying that, and that's not a typo. The reason I say beta to beta bar is I'm changing from the beta coordinates to the beta bar coordinates. So I say it's the p beta beta bar coordinate change matrix. Coordinate change matrix to go from beta to beta bar coordinates. I mean, we can be more explicit about what that matrix is. If you look at it, what is it? I mean, how would you actually find that matrix, that change of basis matrix P? What would it look like? So it's the matrix of phi beta bar composed with phi beta inverse. All right. Now, let's see here. So that's like here, you'd have the standard basis EI, right? And so remember, this is the standard matrix of a linear transformation going from Fn to Fn. So to find the standard matrix, we do what? We feed it what? The first column we get from feeding to E1. And then the nth column we get from feeding it what? En, right? What is phi beta inverse of EJ though? Now is a good time for me to remind you, one way we could define a coordinate vector, coordinate chart, is to say that it maps the abstract basis to the standard basis, and then we extend linearly. So like, essentially by definition, phi beta of Vj is equal to Ej, and then extend linearly. That defines the phi beta coordinate chart. Because the V1 through Vn were, I'm assuming that V1 through Vn is equal to beta, of course, right? Still the case. So what's phi beta inverse of Ej? It's just Vj, right? So when you do these compositions, what you've got is you've got phi beta bar of V1, phi beta bar of Vn. But in other words, the coordinate change matrix is the beta bar coordinates of V1 and then the beta bar coordinates of V2, and so forth and so on, the beta bar coordinates of the nth thing in the beta basis. That's a formula which is often presented in other textbooks as being the change of basis matrix formula. To find the change of basis matrix, this p beta beta bar, what you do is you calculate the coordinates of your original basis in the new basis. And you do that for each one in succession to concatenate those coordinate vectors. That's how you change coordinates, by this formula right here. So, by the way, special case over here, don't need all that, right? Like, what is this coordinate change formula? In retrospect, here we're doing what? We're changing coordinates from what? Changing from the standard Cartesian, right? To the beta coordinate system, right? So if I need to come up with a name for the standard Cartesian, let's call it gamma. I called it. So really what I have here is P gamma beta in this. So P gamma beta would take the gamma coordinates and give you back the beta coordinates. But, I mean, x gamma is just what? In this kind of stupid case, it's just x again. And so if you look at this, and if you look at that, you can see that P gamma beta is what here? It's just that. That's the change of basis matrix to go from Cartesian to non-Cartesian coordinates. It's easier in the case of column vectors because they're column vectors, so we can do special calculations for them. But for an abstract vector space, you actually have to do a bit more calculation to figure it out. Time flies when you're having fun. I'm worried to look at this. Oh. Finally. If we have a linear transformation, all right, from T to W, from V to W, all right, both of these vector spaces over a field F. And if I have the beta cis coordinates, and if I have beta bar coordinates, and if I have gamma coordinates, gamma bar coordinates, and I had gamma coordinates, for the purposes of my diagram, it's convenient to do this. I could view both of these as mapping down to a copy of Fn, and I can view both of these as mapping down to a copy of Fm. All right? On the one hand, I have the matrix of T, which is induced like so. Like this guy, all right? So that is this left multiplication by, let's say, T beta bar gamma bar, right, would come from this journey. That's how I actually define the red map. Let me give you the formula. And actually, let me go ahead and give you the standard matrix. So that gives me T beta bar gamma bar is the standard matrix of what map? Of the, this one goes last, so phi gamma bar composed with T composed with phi beta bar inverse. That's the standard matrix of this left multiplication by the beta bar gamma bar matrix, like we talked about last time, right? On the other hand, I could take a different path, right? I could travel like so. Like so. Sound effects for free. Let's see here. And this is left multiplication by T beta gamma. So what I want to study is, how are these related? What's the what does it take to change coordinates from beta gamma to beta bar gamma bar, or vice versa? So this guy would be defined by a similar thing. T beta gamma would be, same thing but without bars. How are these two related? pictorially, to get, let's see here, to travel the green path by traveling the red path, what I could do, right, is I start here, right? I go up. I go back down. Then I follow the red path. Then I go up. Then I go back down. Like that. So this up and down, what is that? Well, that's, like it's phi beta bar composed with phi beta inverse. So anyway, let me just go ahead and write the thing down. So what we have is T beta bar gamma bar would be the matrix of phi gamma composed with phi gamma inverse phi one of these needs a bar. Gamma bar inverse, yeah, thank you. Composed with phi gamma bar, composed with T, composed with phi beta bar inverse, composed with phi beta bar, composed with phi Oh, I think I messed this up. I'm sorry. Just a second. Let me just... Diagrams sometimes helpful. Sometimes it's better just to think in terms of formulas. This is probably such a case. So this guy is directly what it's... Let me show you kind of how to do this algebraically rather than with the diagram. Oh, that was a stretch. I mean, I hope this isn't a stretch. So how do I change this? I want to get rid of the bars in like. So the way to do that is to just say, okay, so I'm going to compose that with the identity here, but the identity I'm going to write in a very sneaky way. I'm just going to write it as phi gamma inverse composed with phi gamma. See what I did? I just stuck an identity here on Fn, where that identity, actually it's over here, that identity, Fm rather, right, it's given from going from, gosh, let me keep going and stop trying to explain. Then this is what? Phi beta inverse composed with phi beta. I'm inserting the identity, hopefully logically. Does that make sense? T goes from where to where? Think about T for just a second. T takes something in V, maps it over to W. Does gamma eat things in W? Yes, it does. Goes down here. Gamma inverse goes back up here. Phi gamma bar goes back down here. Okay, good. Yes?
So like what you're saying is like even though you stick the identity in there, and pretty much like the identity is just like theoretically like kind of like a one.
Yeah.
Like it wouldn't matter as far as like if we did the operation on matrices, but just like for the sake of like making sense.
Oh.
The directional path, like it would matter the identity. Like.
Well, I mean, I want to put the right identity in the right place, otherwise it doesn't make sense. Like I cannot insert. I can't insert this. This is the identity on Fm, right? This guy is the identity on Fn. And I can't switch these because M and N could be different, and one would make sense one place and wouldn't make sense the other place.
Yeah. Where like it doesn't make sense here, like when we think of that in terms of space as a thinking, but like if we did like the matrix algebra, it would make a difference.
I mean, if you're asking if there are other ways to look at this, then absolutely. Now, I will say this. So we have this composition of maps, right? Some of these are column vector transformations, some aren't. But if you look at it this way, let me just, and function addition is associative, right? So I can group these however I want. In view of that, this, and this, and this, these are all transformations from column vectors to column vectors. That means that I can use the thing I proved the other day, remember? The matrix of the composite of column vector transformations is the product of the standard matrices of the transformations which are composed. I can use that here to rewrite this as this guy times this guy times this guy. Which I would point out to you is exactly P gamma, gamma bar, the matrix of T with respect to the beta gamma basis. And then over here you've got the coordinate change from beta to beta bar, I believe. No, other way around, beta bar to beta. Notice that the letters in the definition of the coordinate change matrix, notice the juxtaposition of the bar and the unbar notation. I'm trying to be careful about that. This is not a typo. And it is important to distinguish one goes beta bar beta, the other one goes gamma gamma bar. So, going back to here, right? If you wanted to relate the standard matrix T, right? Well, let's say the non-standard matrix related to the standard matrix how? Well, we would say it would be what? It would be P, if we believe this. So I'm sorry, I'm having a notational. It's kind of blowing my mind. If you don't mind, I'm gonna. Fine, I'm stuck with this. Dang it! I should have called this beta bar if I'd known. Idiot. Anyway, it's beta, so I got to deal with it. Gamma, beta, standard matrix, which is, I'll just call T gamma gamma for the purposes of making it clear the pattern. And then P what? My brain is going to explode. Beta, gamma. All right. Now, gamma, the standard matrix again. So P gamma beta is what? Beta inverse? Because we figured that out. And this would be the standard matrix, which we usually just call T, like so. And then what's P beta gamma? Beta inverse inverse, just beta. So here we go. This is probably the most important subcase of this, is to find the non-standard matrix of a linear transformation. So here I'm talking about T being a linear transformation from, say, Rn to Rn, okay? This is the relation between the non-standard matrix and the standard matrix, just like that. Again, column vectors for the win, we don't actually have to calculate these rather complicated things for this case. There's a nice shortcut formula. I just found it for us right there. Es bueno? Oh, I guess. That's the thing, is if gamma is the Cartesian coordinate system, our notation is that T gamma gamma is just T with brackets. But of course, the Cartesian coordinate systems is nevertheless. Oh, any questions about this? Because I'm about to cover it up. Coordinate change is hard. It is the hardest topic in the entire semester, I think, without question. This is difficult, all right? There's really maybe only one other thing I can think of that is as difficult as this. But I won't talk to you about that right now. Where was I? So if you find this challenging, well, you have lots of good company, all right? But it is, of course, an important question, right? Because when we work with abstract vector spaces, how many different choices of basis do you have? I will eventually find my linear algebra. Like, this Windows 10 is too smart for me. It keeps reorganizing my folders according to the logic with which it reorganizes my folders. I do not understand. Like, whatever happened to alphabetical? I think that was a good way. All right. Oh. So Adam had asked me about. Oh, please tell me I have. Phew. I was worried I didn't have my adapter here. Oh, sad. Sad. Not you guys, me. Let's see here. So Adam asking the question basically, how to find isomorphisms. I mean, it's almost the same question as how to find a basis, really. See, because if you can find a basis for the space in question, then you can find an isomorphism, right? But sometimes there's other things, like, for example, find an isomorphism, say psi, mapping P4n over the reals to, say, 2 by 2 matrices of polynomials. This is a fun one. So what I would do here, I'll tell you what, I'm actually going to find it more convenient to find the inverse map. So phi inverse of f of x, g of x, not comma, h of x, I of x. What would I do? I'll get a started f of x plus what? That's almost right. But notice that I'm trying to map into a 4n. Oh, and is my counting right? Maybe, does this even make sense? Let's just check a base case for a second here. So like, is P4 of x the same as, is that isomorphic to, say, well, we have like ax plus b, cx plus d, ex plus f, hx plus I. I mean, or have I think I have not, I don't think I've done it quite right, because I would need 4 times what? 4 times, I think the 4n is wrong. I think I need to do 4n. I mean, I can either keep the 4n here and do what over there? N minus 1, maybe? then that would make sense then. See, then I'd have p, if I just have constants here, then I have the right kind of dimensionality. I need an n-1 here, otherwise it doesn't make sense. Okay. So with that, f of x is what? F of x is something like a0 plus a1x, right? Plus da-da-da, plus an minus 1 x to the n minus 1, right? So all I do, guys, is I do x to the n, right? And then plus what? This, and then this would go from like x to the n power all the way what to x to the 2n minus 1, right? Yeah, I think we put x to the 2n here. X to the 3n I of x. And that would go from the see, I'm not sure my counting is quite right. I may be off by 1 or something here. Let me just put some kind of air quotes on this. This may not be quite right. But you see the idea? I mean, the point is you could do something like this. There's no, I mean, it's just creative. You don't have to do coordinates or calculations or something. It's just inventive, right? There are examples like that out there. But most of the ones that you'll face are not so complicated, right? Like maybe you want to find the isomorphism from, I don't know, let's say 2 by 2 polynomials and two quadratic polynomials with complex coefficients, and say are 2 by k for some k. Then what would that? Hey, cool. So you want to find an isomorphism between these. What would you do? So you're looking for like phi of P2C looks like what? Like ax squared plus bx plus c, right? Where a, b, and c are what? The complexes, right? So what I would do, I'm looking, and I need, so how many real dimensions here? See, this is actually, this is six dimensional over the reals, because each one of these, I mean, a basis for this is what? 1i x, ix, x squared, ix squared, right? That's a basis for that space. So I don't know, what I personally do is just to kind of think about how can I rip off things from this to get the kind of object I want. So this would also be, I mean, to be more precise, this would be what? This would be psi of a1 plus ia2 plus b1 plus ib2 plus c1 plus ic2, right? And once I do that, then it becomes really, what's my two rows, how many columns? Oh, yes, thank you. Oh, yeah. Not really. I mean, yes, but fine. It's just stupid blue marker. I gotta throw this thing out. Okay, so what's the what could you use for an isomorphism here? You just map the coordinates to like, I mean, I just see it. I don't know, a1, a2, b1, b2, c1, c2. I mean, that's one of many, many choices. You could prove that that's an isomorphism. You could prove that that's invertible, that it's linear. Now, of course, I mean, maybe a better way to do this would be to say, so that's a basis, right? So I can just say, I'm going to define the isomorphism by psi of 1 is E11 psi of I is E12. Psi of x is E13. Psi of Ix is E21. Psi of x squared is E22. And finally, psi of Ix squared is E23. 23 rather. And then extend linearly. If I extend linearly, automatically linear, nothing to prove. And if it's a mapping of a basis to a basis, it's certainly invertible. So that suffices to give an isomorphism, right? I mean, that's the same formula. Extended linearly is the same formula. So what's the best way? I don't know. You got lots of choices. Yes?
We learned that if it's bijective, it's invertible. Is that biconditional? Like if it's invertible,
Yeah.
it's also used by
Yes. Yeah. If you can't have invertibility without bijectivity. Yeah. By the way, here's an example, guys, of coordinate change. I just want to show you one thing, and then I'll shut up. So in here, I actually have an example of a linear transformation. The linear transformation is this thing, t of f is f of, what is that, I? And so I look at a linear transformation from quadratic polynomials to the complex numbers defined like so, and I find the standard, find the matrix of t with respect to a particular choice of basis. And then, on the next page, I actually look at a different basis, and I find the matrix of t with respect to a different basis. I think I'm doing something more than that, though, here. Oh, yeah. Well, so the change of basis matrix in the domain is 3 by 3, because the domain's 3-dimensional. But the range, on the other hand, is complexes, so it's 2-dimensional. So you got a 3 by 3 matrix on the one side. Like this and that don't have to be the same size. See, 3 by 3, this is 2 by 2 in this example. And I show, in fact, that you get the same formula back again like that. So I do have an example in the notes here for you. The other thing I would say, Adam, is that, more to the point, this theorem is super useful. Don't neglect this theorem. If you have a mapping from a vector space to itself, or from a vector space to another one which is of known dimension, finite, it's surjective if and only if it's injective, if and only if it's bijective. So if you get any one of those three, you got the other two. That is very nice to know. And finally, I have oodles and oodles of examples of isomorphisms in the notes that you should not neglect because they might help you out. I mean, what I was showing you was just a sample. Come on. Oh man, I was going to show you. Curses. So like here's an isomorphism from, complex numbers cross real numbers, 2 by 2 matrices, to 2 by 3 complex matrices. And so if you look at these examples, I got like a bunch of them, and they should give you a better sense of how to find isomorphisms. And don't be scared by isomorphisms. It's not really that complicated of a question. It's just you have to come to terms with it to be asked. Anyway, with that, I will shut up. Sorry for going over. Oh man, no determinants. Arrgh.
We can apply it to that problem.